Thanks everybody for coming to the presentation, and I'm gonna discuss some of the preliminary results we obtained last year. The research we're doing to try to estimate the demand that transforming a diesel mine into electrical mine could have underground. Based on the use of battery electric vehicles to replace diesel vehicles for mining application. Okay, so the presentation is divided in 4 blocks. We'll first discuss the objective, which is what we're trying to achieve. Second, methodology, which is how we go about it. And then we present the results and we discuss a little bit of the possible next steps for this. So in terms of the objectives, what we're trying to do is to couple a vehicle class. So a vehicle class in mining terms is the type of vehicle which is, for example, a haul truck, load, haul and dump, which is also called scoops or LHDs equipment, which are usually the ones that are used to load the haul trucks with the materials. And we couple this vehicle class with this duty cycle. In this case, the duty cycle is the combination of the load, the speed, the grade, the distances, and the pauses that the vehicle will experience while it's working on the ground. And also we couple it with the charging strategy, which is, in this case, the charging strategy can be onboard charging, offboard charging, whether you do opportunistic charging or not, or for example, swapping batteries, or the other alternative that exists right now is also known the fast charging. So there's a few ways of charging the batteries, so you can replenish the energy that is taken away by the vehicle while it is performing their duty cycle. And all of these, the idea is to couple these 3 concepts to estimate the electrical grid power demand over a shift for an underground mine application of these battery electric vehicles. So the vehicles classes that we're gonna center on are personal carriers and prime movers, as they can represent over 80% of the diesel consumption of an underground mine. The duty cycles that we're going to use are specific to each vehicle class, and they're based on mining applications or our knowledge of mining applications. And the charging strategies that we're going to use, for both the battery size and the charging strategy used for that each battery size, are going to be according to what the OEMs have available in the market per class of vehicle. So we're not trying to estimate what will be the need. So it's the other way. We're going to take what's available in the market right now and try to apply it to the different uses that it has in an underground mine to estimate the power grid. And the target is to estimate this power grid for a 12-hour shift per class, and then aggregate that for all the classes and the number of vehicles of each class that a mine could have, to estimate these power grid demand for the shift for the mine. Okay, there's a few steps that we need to develop in order to get there. So the first one is we need a way to estimate what is the energy that the vehicle is going to use for a certain duty cycle, and that's what we call the energy consumption model. So we first need to calibrate this model, and ideally you can calibrate this model with data from the field test. If not available, you can also look at equipment specifications, or worst case literature, or a combination of the 3 depending on what's available. And this approach allows for simulating. Once you have a calibrated energy consumption model, you can simulate different duty cycles. The limitation of these approaches can only be applied to vehicles that have a calibrated energy model. Okay. In terms of how we go after from the energy model to the power demand, the power of the grid can be estimated based on the charging of the batteries. So And for that, we need to know when the charger is being used and for how long, and what's the demand of the power of that charger. So for each vehicle class, we estimated first the power that how the vehicle will deplete the battery over time, and then we also estimate how the charger is going to be used to charge that battery over time. And for that, we consider also the different charging strategies, such as regular charger swapping, again, according to what the OEMs have available in the market. And we also include charging conditions such as the minimum state of charge of the battery and per vehicle class, and maintaining the initial state of charge per shift. What this means is that if an operator got to the vehicle at an 85% of the battery, it is expected that by the end of the shift, when the next operator is going to come to take that vehicle, it's going to find it at the same level. Okay. Here's the flow diagram of all those different steps. So as you can see on the left side, we have either the inputs are either the vehicle OEM specifications, the CanmetMINING field test data that we have, and the literature data, which could be first principle theoretical estimates or field tests that we use to calibrate the energy consumption model for each of the categories. So in this case, is the man carriers, LHDs, and haul trucks. And then on the side, we define duty cycles for each one of these categories. We also define schedules on how these duty cycles are going to be applied during the shift. And that we use to calculate the battery power and energy demand simulation during the shift for that particular category. And then based on that, we also define the charger power and energy demand during the shift, and with the quantities of each type of equipment, definition of the duty cycle they're going to have, and the quantities, and we can aggregate all the charger profiles over the shift, and then we can obtain the graph that is shown here. I don't know if you can see my mouse moving right there. And that is basically the end goal of the presentation, which is to obtain the grid power demand, in this case in megawatts, over the shift from the start of the shift at time 0 to until the end of the shift at time 12 hours. Okay. So first vehicle class, the personal carrier. In this case, we have done some field testing with CanmetMINING a few years ago. So for these two pieces of equipment, in this case, the relay and the Rockion R400, there are vehicle specifications available. These normally include the payload, operating weight, total weight, or gross weight, which is the sum of the payload and the operating weight or empty weight. They also include the motor power and the battery power, which can be some of the limits that the vehicle achieves when it's trying to perform work. On the other side, we also have, as part of the specifications, the charging specifications, which usually describe what type of charging it has, whether it's on board or off board, the power of that charger, and then for the range of charge, so the bottom and upper limit of the SOC, what is the time to charge from the bottom to the upper limit. And also included in these specifications normally is the battery energy expressed in kilowatt hours. With the specification data, or with the in this case the field test data, we use that input to estimate the following three parameters: rolling resistance, vehicle efficiency, and auxiliary power. So based on the first principle power and energy equation for vehicle motion, the key inputs to calculate the power and the energy consumed by an electric vehicle basically require your great load speed distances or the time that you're performing that movement. And also these three parameters here: the rolling resistance, vehicle efficiency, battery to wheel efficiency, and the auxiliary power. So if you have all that data, you can then estimate the power and the energy that the vehicle is going to need. So for these two vehicles in particular, we did the work of estimated these three parameters based on what we measure in the field in previous research, and now we can use it to simulate other duty cycles for these two particular vehicles. Okay. Just to clarify, these parameters were not measured in the field. These were inferred from the data measured in the field. Okay. So next step is to define the general duty cycle. So how the vehicle is used. So these type of vehicles are usually used to transport people from one side to the other of the mine site. So in this case, the most demanding use of this vehicle is what is called the shift supervisor. And this person, by regulations, has to visit every one of the workplaces of the workers reporting to him or to her within the shift. So that's why usually this is a vehicle that circulates the most for these kind of vehicles in the mine. So that's why we decided to go with this one. In terms of the proposed duty cycle, what we decided to do in this case was that the travel was going to be done fully loaded when going downhill, and travel empty uphill, and do that travel at 10 kilometers an hour in both ways. Although this is an input that we decided, it might vary, but we decided to that it could be a representative of underground operations, although it's not unique. There could be alternatives to this. The route used in this case, or suggested for this exercise, was 500 meters from parking to ramp portal. We tried different ramp distances from 2 to 10 kilometers, so 2, 4, 6, 8, and 10, and then another 500 meters from the ramp level access to the level destination. And we use a 15% grade on the ramp and a 2% grade on the surface and level access, mainly due to water management design. This could go up to 3% too, but that's usually observed underground. And we also consider that the shift supervisor would have 1 hour to stop after each cycle, which alternatively allows it to stop for an hour in total within each cycle, assuming that he had to come down, inspect the area, discuss with the worker, maybe provide some supplies. So, and then we also decided that this cycle had to be performed as many times as possible within the 12-hour shift. So for the work schedule now, so how many of the 12 hours can you actually make use of during the underground shift? So first we started the shift at time 0. We allowed half an hour just for the operator to arrive and do the pre-operational check and start the equipment. Then there will be 10 hours available to work within this 12-hour shift, and then there will be half an hour at the end of the shift for the operator to vacate the mine before the blast, and then an hour for the blast and fumes to clear and get the approval to re-enter the mine. Okay, so these right here, just as is, the 12-hour shift now got turned into 10 and a half, in a 10-hour shift, just because of the other activities that are needed before actually being able to start using the equipment. In terms of the charging strategy, the first criteria is that when the next driving cycle will bring the level of the battery below 20%, then the operator will have to stop and charge it. And we impose a second criteria, as we discussed initially, is that when the level of the charge at the end of the shift would not match the start of the shift, then we would force an additional charge just to make sure that that happens. And both criteria got triggered when the equipment was not working. So we assume that the equipment would have access to a plug in order to be able to charge. And yeah, so after adding together all the components that I just mentioned, we were able to generate on, as I'm presenting on the left side, the graph of how the battery depletes over the shift. So on the y-axis, I have the energy of the battery, and then on the horizontal, I have the time of the shift from 0 to 12 hours. On the right side, we have so how the charger performs during the shift, and on the left side is how the battery performs during the shift. So there's a few events that you can see on the graph. So on the left side graph, when you have a flat line, that's when no consumption or charge or regen is happening to the battery. So that's when that's a flat line. So usually it's the 1 hour break when it's not being used for charging the equipment. Then you have these little bumps there in between the flats. So when it's going uphill, when the curve is going uphill, that basically means that the equipment is going downhill and is charging via regenerative braking. And the other uphill is when the charger is being used. So there's two mechanisms for energy to go back into the battery, which are either plugging it to the charger or driving the equipment downhill and getting energy through the regenerative braking. Okay. When it is observed that the almost flat line or inclined towards down on the battery graph, that usually means that there's a discharge of the battery energy via by the use of the equipment, either it's in the flat or uphill terrain. Okay, and then based on these, we can generate the graph on the right side from the charger power graph from the electrical grid to the battery, and which basically it's either off or on, and when it's off, there's no power flowing from the charger to the battery. When it's on, it's flowing at full capacity as defined for each of the chargers for each type of equipment. So we start doing these for each one of the different ramp length. So, and we obtain the two graphs for each one of them for each type of vehicle. So as you can see here, the 2 kilometer, 4 kilometer, 6, 8, and then 10. And then basically right now, what we have generated is a unique combination of a vehicle class, duty cycle schedule, and charging strategy, and what is to be expected of that one, which is kind of like our unit charging demand, okay, which can then be used in a mix for a certain mine operation. So here's the table that resumes the simulated scenarios from 2 to 10 kilometer ramp for the rock and man carrier, personal carrier, sorry, and within the 12-hour shift, and it shows how much energy can be needed during that time for that specific piece of equipment, distances that were covered, number of cycles that were achieved, a cycle being from the start going down an up ramp and going back to the same point, and what is the distance for each cycle. We then do the same with the relay, calculate the same energy demands and charger power grid demand for the different ramp distances, and then generate the same table. Usually the limit of the distance that the vehicle can travel is the distance that the vehicle can travel in the ramp, and basically depend on the size of the battery, decline of the ramp, and the load of the vehicle, we can estimate that. But in this case, both equipment can drive up to 10 kilometers in this ramp. Okay. So what we learn from here is that there's several inputs required for each one of these simulations, as discussed previously: speed, grade, load, distances, the schedule, the battery power and energy, charger power and location, charging strategy, the logic used to charge, among others. And of course, this allows for almost an exponential number of what-if scenarios that can be generated with the combination of these different variables. And all of these can affect the charge that will be required and available as a result of the grid power demand over time. However, these are all estimates based on the number of charges that can be simultaneously be charging at any time. So as a result, even if you have a significant number of variables that you can mix for different what-if scenarios, these are all covered in an envelope, which is basically the number of chargers by the power of chargers and when can you use them in the shift. Another thing that I'd like to clarify at this point is that the queue process for traveling in the ramp and or for charging were not considered in this analysis. At this point, we did not went to that level of detail in terms of the simulation. Other things that we observed from these analyses is that at least for the two personal carriers simulated in this study, both were able to perform the suggested duty cycle. We didn't get to a point where one could not do it, but we also limited the duty cycle so they both could perform them with the batteries considered, which in this case were 48 kilowatt hours and 100 kilowatt hours. And these two batteries had enough capacity to store more than the energy required for the suggested duty cycle, and enough time and charging power to replenish that energy during the shift, either as it was needed or in working breaks. So that's for the personal carrier. The next category now is what is usually referred as LHDs, or load, haul, and dump vehicles. There's, at the time we did the study, these four alternatives were the ones available in the market. So we just decided to go with what's available. So we had a couple of options from Epiroc, one option from Sandvik, and then there was the other option from Caterpillar. Interestingly enough, these options also had different charging strategies associated. The Epiroc ones, you could either charge on the spot or swap the batteries. But with the use of a crane, the Sandvik one was equipped with what is called the self-swapping capability that allows the equipment to drop the battery and go and grab another one. And the Caterpillar, they decided to go a different path. There's no swapping for the Caterpillar. Is what they call the fast charging, which can be half megawatt or full megawatt fast charge. So here you can see the vehicle specifications. So payload, empty weight, gross weight, motor power. In brackets is auxiliary power. So this is motion motor power, and also the auxiliary for the movement of the buckets and steering. And then also battery power continuous for whichever were available. And AM is not available. Same for the charging specifications. And Then, based on the specifications that we found for this piece of equipment, we use that as an input to calibrate the energy model, and here are the results that we obtained. However, the first thing we observe is that the vehicle efficiency, for example, was not consistent between OEMs, and same for the rolling resistance, at least for the CAT. And also, it's good to indicate that these results are only applicable to the hauling portion. The load and the dump power needs are not included in the specifications of the OEMs. So these results, for example, the efficiencies that were over 90%, that does not really match with what we have observed in the field for these and other classes of vehicles. So in the case of the LHD, we're fortunate that we had some data from a field test that we had performed. So we, instead of using the specifications, we decided to use the parameters that we had from that field testing and the energy model calibration that we performed. And also with that test, we were able to gather the information of the energy needed for the load and the dump for each cycle. And in terms of the duty cycle considered, there's a few different ways that this equipment is used in a mine site, either to empty a development, freshly blast development phase, or a stope, a production stope. So from the development phase, that can be it can be in a level or in a development ramp, and then from there the material needs to go either to a truck, or in the case of the level, or to an ore waste pass, and in the case of the development ramp, to a truck, and then that gets combined also with whether it is just charge at the end of the shift, plus when it's convenient during the shift, or if the battery is actually swapped, and then the equipment keeps working. In terms of the proposed duty cycle, we assume that it was going to be traveling 100 meters from the level to the ramp axis. There would be a variable, a 15% incline ramp with this variable distance from 200 meters to 600 meters at about 11 kilometers an hour. That speed came from what was observed in the field, and that it was going to go empty downhill and then come back fully loaded on the return. And then it was going to go 100 meters from the ramp into the load area and back. And we also assume the time and power for process for the loading of the bucket and the dump of the bucket. And we repeated this cycle until the battery reached the arbitrary minimum of 15%, as we observed in the field test. And we kept the cycle or bucket count. And at the 15%, we either send the equipment to charge or to swap the battery, and perform as many cycles possible within the 12 hours. And the work schedule is the same as presented for the mine carrier. So there's 12 hours, there's half an hour of reaching the equipment, 10 hours of work, half an hour of vacating the mine, and an hour of blast clearance. And we decided to exclude the lunch breaks for the LHD driver in this case, as in the charging strategy that in this case we consider, which is the first one, which is just a regular charge. While the vehicle was charging, they could have time for that. So we generated the graphs I've presented here for the different ramp distances, both the energy consumption and the charging grid power. And then also generated the table with the summary of the results. And We then did the same exercise. So the first exercise was just for the battery charging, which might not be the most efficient use of the LHD, but it was a good reference to see if that type of charging strategies could be used or not at a mine site. As we observed in one of the tests that we did, it could actually be used for the blast headings for development, but for in case of making a stope, an equipment that could be working the whole shift was more suitable in case, which would be this case of the swapping charging strategy. So we generated the graphs for these scenarios too, and the table with the summary of the results in terms of energy, distance, number of cycles, and the distance of each cycle. So interesting things to observe in both cases is that they're able to do more than 30 cycles or 30 buckets, which is usually the bucket count for a freshly blasted heading. So that means that they can achieve the expected performance in the shift. We also observed that longer ramp increases the energy use and charge and increase active time. So there's less puzzle observers, and as a result, more time, the equipment has more time to consume energy. In terms of the summary of the results for the LHD, it will depend basically on the type of application, effective LHD work demand. So charging, we didn't want to dismiss these charging strategy, the direct charging. And as we mentioned, it's a valid option for attending freshly blasted development headings. But swapping would be a preferable option for a stope that requires a complete shift to empty and to generate the production for the mine. And yeah. The other things that we observe here is that in terms of the number of batteries needed for an LHD, in the case of swapping, 2 batteries would be enough for the LHD to work, as the energy is consumed at a slower rate than the battery was charged. As the distances between the working areas and the charger increase, the effective time to work will be reduced. So that's a consideration where to get your charging base and have them as close as possible to the working areas. And in terms of the assumptions that we have in the simulations, we assume that the scoop would always have available a place where to dump the material. So basically, we didn't add additional waiting time either for the whole truck or the means of carrying the material after the scoop. We just assumed that it would have a place to put it, so it could just keep working continuously. Okay. The reality of a mine could be different. We have seen where the scoops have to wait for the whole trucks a significant amount of time, and in that case, this would reduce the time that the scoop was actually operating the shift, and also, and as a result, we resolved the energy expected to be consumed by that LHD during the shift as well. Next category, the whole trucks. So I'm going to go a little bit faster here just to make the times. How much time do we have, Grace? We're good there?
I think we have 20 minutes.
20 minutes? Oh, I had less. Okay. And so same, we look at the whole trucks, the battery electrics that were available in the market. In this case, there's even less alternatives. There's one by Epiroc and a couple by Sandvik. And again, this is for the underground exclusive mining environment. There was a couple more developed by Artisan, the Z40s and Z50s in the past, but after Sandic acquired Artisan, they continued with the one with the 50-ton capacity. I think they're not continuing with the 40-ton one, and instead they decided to go to the 65-ton, which is the one shown at the bottom. Again, we look at the specification for each vehicle. We also look at the charging specifications that came with those different vehicles, and we use the data from in this case, at the time of developing these studies, we didn't have field test data for whole trucks. We do have now, but we haven't got to the point of using it to calibrate the energy model yet. So what we did at the time of the studies to use the data we had from both the OEM specification and data that we found in literature. And the interesting thing here is that when you use the data from the specs to calibrate the model, the vehicle efficiency is much more in a close range as opposed to what we observe with the LHDs. And the range that we observe here is also a lot closer to what we have observed for different vehicles in the field. So that was interesting. I thought it was interesting to mention. And also that these results only apply to the hauling portion. Damping needs to be added to the energy consumption model. So from the test that we did in the field, we extrapolated the data to try to assess what would be the parameters for rolling resistance, vehicle efficiency, and auxiliary power. And they were not too far from the ones we observed from the vehicle specifications. And we did an exercise after this, is that we estimated the auxiliary energy for each one of the whole trucks based on their weight. And as we saw a correlation between the LHD and the auxiliary power in the test that we did in the field. But we also did the exercise to see if that auxiliary power consumption was actually significant or not for these type of vehicles, and the result was that it was less than 3%. So it could be considered negligible for these type of analysis. The proposed duty cycle for these equipment is the route that has 200 meters from the level to the ramp. Then the ramp has variable distances, 1, 2, 4, 6 kilometers, and then another 100 meters from the ramp to level access where the truck is going to be loaded by the scoop or LHD. And the ramp grade considered is 15%, and the surface and level access grades considered are 2%. And each cycle considers time to load and unload. And again, we try to perform as many complete cycles as possible within the 12-hour shift, which is the 10 effective hours. And we repeated the cycles until the battery SOC is 15% and keep the cycle count. And work schedule, as mentioned before, is the same as the relays or the personnel carriers. And in the case of the whole trucks, we did not consider time for lunch. And because these operators are usually paid by bucket delivery, so from observations in the field, they don't really take time for lunch. They just keep going. Okay. And then we generated again the graphs for each type of ramp, and both for the energy consumption and for the charger grid power profile during the shift. And in this case, we did two scenarios for the whole truck. We did the regular charging and we did the swapping. We just did the regular charging to show that really there's no point on doing regular charging with a whole truck, because almost half of the shift the truck is charging as opposed to be working and moving the production of the mine. But here the results for the charging strategy applied to the whole trucks, and then this is the results now with the swapping strategy, which is the one more commonly used for whole trucks. The one thing we started observing for the whole trucks is that, and that's where you see on the right side here on the charging, that there's these spikes that started to show. These indicate that a third battery is required for the charging, mainly because the truck is consuming energy faster than what the charging stations can replenish the energy in batteries. Okay, and as the ramps gets longer, that becomes more evident. Okay, and here we have the summary of the results. So in terms of what we observed for the simulations of these class, definitely the swapping maximizes the availability of the whole truck during the shift. The battery size currently limits the application range of the whole trucks to 6 kilometers, at least for the one that we use in the case study. And with as I indicated, with longer ramps, the third battery could be needed to complete the swapping process, as the energy is consumed faster than is charged. However, that is based on our assumptions. In a real time, in a real mine, there could be waiting times for dumping or for swapping. There could be also traffic interaction, and there's different conditions. There could be a lesser payload due to the density of the material, and more powerful grid charger batteries combinations could be available. So there's a number of reasons why that might not be observed in the field, but it was observed in the simulation. So basically, after we did all these simulations, we then started picking which ones we're going to combine to generate the grid power demand profile. And so just as an example, for I'm showing here for the whole trucks, we have the 1, 2, 4, and 6 kilometers ramp, different scenarios for charging and energy consumption. And then we decided that we're going to have 4 trucks on 2 kilometer, 4 and 4 kilometer, and another 4 and 6 kilometer ramp duty. So from an example mine that we have from field test, that mine had 12 whole trucks, so we decided to replicate the same amount of equipment from diesel to BEV. And we did the same for the LHD that mine site had. So and for the personal carrier, so the mine site had 12 whole trucks, 9 LHDs for those 12 whole trucks that were operating, and I think it was about 24 personal carriers. So we distributed them across the different scenarios that we had already pre-calculated, and we used them to calculate the grid power demand. And I think I'm going to leave the presentation here, Grace, so it allows at least 10 minutes for questions.
Great, thank you. Do you have any questions? But otherwise, I can start with one. Thanks, Enrique. Very impressive and comprehensive presentation and research. I have one question. Basically, is because several years ago we discussed about all these trucks, which is expected to be used in underground mines. Is it correct?
Sorry, what is the question?
I mean, this all the EVs is going to be used underground, right? Yes.
That's
Yes, that's actually I was told by you and Michelle, which is the ventilations in the underground mines, which is quite critical important. So my question basically is if the underground mines actually implement this EV and EV charging, and that is actually will it give this kind of overload to the power grid, which is maybe result to this ventilations which is stopped to work because of this charging and overload.
So there is a couple of things there. So if you change diesel equipment by BEVs, in theory, you could reduce the ventilation required for the mine site for the same number of vehicles and the production expected. However, that has a few conditions, right? So first, you need to be able to segregate areas or to be able to selectively decide the amount of airflow that you deliver for each kind of equipment. Both of them are not straightforward. So if you're thinking like brownfield, where you're gonna bring these whole tracks to this place or replace the diesels, it's not going to be straightforward to see the reduction on the ventilation energy demand. So there could be an issue there where adding all these extra BEV demand might actually overload the grid that is available for that the electrical grid available for that mine. But again, that is a case by case study that needs to be done. It's hard to tell. Like we did a study, one of the first studies that we did for this example mine that I'm referring here, and in their case, they did have the 4 or 5 additional megawatts power remaining in their grid. The main issue for them was not really if they could absorb it. It was one of the main issues was if that was the best use for that additional power for them. Mainly because you can decide to expand the mine site, the mine deeper, and that will require more energy for ventilation. So there's a few different aspects that have to be considered. But yeah, for brownfield, definitely introducing BEVs is an additional electrical demand and has the potential to overload their grid as it is before introduction.